in the January 2022, this year, as a means to drive technology development and deployment in affordable and clean energy space, especially for underserved sectors of Indian society. The center's efforts span clean energy generation and storage, energy efficiency and economy, end-use optimization, and allied socio-economic challenges, particularly in peri-urban and rural regions. The center is supported by the Principal Scientific Advisor PSA Office, Government of India, and CSR support from companies including Honeywell Infineon. To foster an inclusive technological innovation ecosystem in these areas, the center is looking for related problem statements and innovation or innovative solutions through an innovation challenge. It is called as Catalyze Tech. The problem statements may be from sectors such as livelihood, agriculture, allied agricultural industries, resilient micro businesses, built environment, and health, education, etc. So submission form for the Catalyze Tech problem statements and solutions, I will put it in a chat box. Now I would like to introduce the guest speaker today for today's talk, before inviting him to begin the talk titled Pinpointing Transient Processes and Inhomogeneity within Batteries, Leading Design of Rechargeable Alkaline and All Solid State Lithium Cells. So Professor Josh Gallaway is a DiPietro Assistant Professor in Chemical Engineering at Northeastern University, where he has founded the analysis of complex electrochemical systems laboratory, SS Lab. He received his PhD in chemical engineering from Columbia University in 2007. Working with his advisor, Professor Scott Calabrese-Barton, he characterized the electron transfer rates of enzymes embedded in oxygen-reducing hydrogels. After his PhD work, he completed a postdoctoral appointment with Professor Alan West, also at Columbia, studying non-uniform current distributions in submicron interconnect features for semiconductor industry. He then joined the newly formed City University of New York CUNY Energy Institute in a research position funded by Wallace Foundation. There he worked on an ARPA-E funded project headed by distinguished Professor Sanjoy Banerjee, which resulted in the spin-out company Urban Electric Power. His recent research has focused on using high-energy synchrotron techniques to visualize non-uniform reactions within battery electrodes. He received the National Science Foundation NSF Career Award in 2021. So I request Professor Josh to please share the screen and start the presentation.
Thank you so very much. Thanks everybody in Dharwad for coming to my talk and watching me. Happy Friday night. It is Friday morning where I am. I'm in Boston. And Professor Patil and I used to work together in New York City at the Energy Institute, and we shared an office. So that is how we know each other. All right. Now, I believe I'm sharing my screen, and here is my talk.
Yes.
Let me know if, okay, you can see it.
Yes.
So I'm going to talk about pinpointing transient processes and inhomogeneity within batteries. And really what I'm talking about is what goes on inside batteries. Batteries are closed systems. You think of them as some thing that you put into a device, but there's a lot of complexity to what goes on inside of batteries. So the first thing I'm going to do is I'm going to do an introduction. And the introduction is the longest part. So I have approximate times here. So you don't think I'm going to go on really, really long because my introduction is long. I'm going to talk about why we need batteries, what my group's research goals are, and a little bit of what I call battery engineering 101. And then I'm going to talk about synchrotron characterization. Then after that, I'll talk about two applications for batteries. So in my group, we use electrochemical engineering principles to design materials and electrodes for energy storage. And that is for two general societal benefits. The first is low-cost aqueous rechargeable batteries for the power grid. The reason we need those, as I'm sure you're aware, is because solar power and wind power are both intermittent, and you need batteries to back them up. The second is all solid-state lithium batteries for transportation and portable power. And that is because we need to electrify the world vehicle fleet so we don't have all of these internal combustion engines making CO2. So our scientific goals in my research group are meant to solve problems that will help us do these things. So the first of our goals is to achieve robust rechargeability of manganese dioxide and zinc. And that is for large-scale batteries for the grid to support solar and wind power. The second thing we do is we work on achieving homogeneous utilization of cathodes in solid-state batteries. And those are for transportation and vehicular batteries. So to do both of these things, we also do advanced characterization for batteries. That is often based on synchrotron techniques. And so we also partner with other people who are making batteries, and we do advanced characterization for them. And this one that's rotating up here is an example. This is a slice of an anode that is inside of an Energizer battery. Energizer is a AA type battery that you buy in drugstores, just anywhere here in Boston. All right, so now I'm going to give some general background on batteries and what they look like on the inside. So like all electrochemical devices, a battery is something that has two electrodes, an anode or negative electrode and a cathode or positive electrode. So each of these electrodes connects to a circuit. So this whole thing has to make an electrical circuit. So it's connected up here to whatever you want to power with the battery. And the current across the battery can flow either as electrons or as ions. So the anode and cathode are both usually porous electrodes. And so I've shown here that these have a white solid material with a gray liquid material in between them. So this general picture of a battery is true for many battery types you've probably heard of. So a lead acid battery, there's a lead acid battery. This is a silver zinc battery, button cell. So this is like a small rechargeable battery. And this is a cylindrical zinc MnO2 battery, where the anode is on the inside of the battery and the cathode is an annular shape around the outside. And that's what an Energizer zinc MnO2 battery looks like. Looks like this. And I'm going to use that as my example on the next slide. So this is some battery engineering 101. So why are batteries complicated? Why do we need people to study batteries? So a zinc MnO2 battery has a zinc anode and an MnO2 cathode. And zinc and MnO2 have capacities of 820 milliamp hours per gram and 617 milliamp hours per gram. And those are things that you can calculate just from the periodic table. Each of these materials can undergo an electrochemical reaction, which is why we can put them together into a battery. Here is the zinc electrochemical reaction, which is an oxidation. And here's the MnO2 electrochemical reaction, which is a reduction. So the electrons are on opposite sides of these two reactions. These reactions are 1.5 volts apart. All right, so we know that 1 gram of MnO2 will be perfectly balanced by 0.75 grams of zinc. So we can add that up and get 1.75 grams. And we know that the MnO2 has 617 milliamp hours. So we divide that by 1.75 grams and we get 353 milliamp hours per gram. All right, so that's like an amount of charge per mass of the battery. Then we take thermodynamics into account. So to add the thermodynamics, we take that number. I've converted it to 353 amp hours per kilogram, same thing. And I multiply times the 1.5 volts. And we get 529 watt hours per kilogram. And watt hour is a unit of energy. So that's energy per mass of the battery. And that's the kind of number that if you're designing batteries, you can take to somebody and say, hey, I've got a battery that has 529 watt hours per kilogram. Will that support your application? Could you use that in, for example, the phone that you're designing or the car that you're designing? But this is a very ideal number. So many other things we need to take into account when we design batteries. For example, inactive components. The anode and cathode need to be separated by something, otherwise they will touch and short circuit. So there's a separator. We also have to put in the electrolyte. We also have to put in current collectors, which are inactive components, and we have to contain the battery in something. So those things that we add all add mass and add volume to the battery. But also, electrochemistry is an interfacial phenomenon. So in this picture right here, the reactions will only happen at these two lines, and this bulk will not react. So we have to make the anode and cathode have a high surface area, so everything will undergo an electrochemical reaction. So we have to make it particulate. Now it's particles. And now we have to think about the particle size, the specific surface area, the porosity of these electrodes, and their tortuosity. These are kinetic and transport related issues. But then we have to think about how we balance the anode and the cathode. So they may not be perfectly balanced, and in many cases they're not. We have to think about the thicknesses of the electrodes. We have to think about any additives we put in, and we have to think about the electrolyte volume that we put in. So when you consider all of these things, battery engineering looks to be difficult. So the porous electrode is a very interesting thing in electrochemical systems, and it is designed that way to allow transport. A porous electrode that has both solid and liquid phases allows two types of transport across the battery. Ionic current can travel in the liquid, and electronic current can travel in the solid. So these are a couple of electrochemical reactions. This is the cathode reaction in the zinc MnO2 battery that I just talked about. This is a cathode reaction in a lithium-ion battery. So they have some similarities. They're both intercalation reactions. So this one is an intercalation of protons. This one is an intercalation of lithium ions. So these reactions both involve electrons on one side of the equation and ions on one side of the equation. So there's an OH minus and an E minus. And on this equation, they're actually on the same side. There's an E minus and there's an Li plus. But both of them involve electrons and ions. So those electrons and ions have to come together to do whatever reaction has to happen. And so, for example, ions can travel to this site right here, and then an electrochemical reaction happens there, and then the electrons travel the rest of the way across the cell. This is a kinetic expression to describe a reaction like one that would happen right here. This is called the Butler-Volmer equation, and it's a very standard kinetic equation for electrochemical systems. Current is exponentially related to the voltage. So it's an exponential relationship, and it makes your equations complicated. The coupling of this transport and the kinetics controlled by this exponential equation, can lead to interesting inhomogeneous, non-uniform reaction distributions in an electrode. That's the kind of thing that I'm interested in, and it's what makes electrochemistry very interesting. Okay. So if you like transport phenomena, electrochemistry is great. So my group uses synchrotron light to study materials inside batteries. And if you've never heard of a synchrotron, it is a type of particle accelerator. Here's a picture of one that's in the United States near Chicago. This is called the Advanced Photon Source, or APS, and it was turned on in 1995. That makes it kind of an old synchrotron. There's another one that we use that was had its first light in the last 7 years, called the National Synchrotron Light Source 2, which is near New York City. So when Professor Patel and I used to work together, I would do a lot of experiments on synchrotrons near New York. So a synchrotron is a type of particle accelerator. It's actually a very small particle accelerator, but you see here it's a big building. These are cars in a parking lot. And it produces very high quality X-rays. So here's one technique that we have done quite a bit at synchrotrons, and I developed this while I was working in New York. And it is energy dispersive X-ray diffraction, and it is special because it uses high energy X-rays. So many people study electrochemical systems with X-rays, but we use high energy X-rays. So let's say we have a battery here, and it's being hit by a beam of X-rays that have energies from 20 to 200 keV, and these are the so-called hard X-rays. These are very high energy. These are the same X-rays that are used if you go to an airport and have your luggage scanned and it goes through the conveyor belt. These are the same energy of X-rays that scan your luggage. So the X-rays penetrate the battery and go right through. This is a very big battery that has a steel case. And we set up a detector that's at some fixed angle. And most photons go straight through the battery, but some diffract, bounce off crystal lattice planes in the materials and go to this detector and light it up. And we can use slits to define this gauge volume and make it very small inside the battery. And then we can scan throughout the battery by moving the battery. So we move the battery over this gauge volume, and it gives us crystal information of the materials in the battery. And we can do this as a function of location and as a function of time. So this is a D-cell battery, which possibly you've used. A lot of these go in, I have young children, and there's a lot of D-cell batteries in all of our baby devices. So we have a chair that vibrates and helps my son go to sleep, and it takes 4 D-cell batteries. So I'm changing these all the time. And if we put the gauge volume at this pin that's at the center of the battery and scan through the anode, and then scan through the cathode, and then out the outer case of the battery, we get results that look like this. These are X-ray diffraction results, and the black marks are peaks caused by the crystalline materials in the battery, and this lets us fingerprint the materials that are inside the battery. So right down here, this is the brass of the pin. Then as we're going through the anode, we see these 5 reflections or peaks right here, and those are zinc. In the separator between the anode and the cathode, we see nothing because there's no crystalline materials there. And then in the cathode, we see these 3 peaks, which are the cathode material. And then the outer cylinder of the battery is actually 2 layers of metal, and we see those 2 materials right here. Okay. So the reactions that happen in this battery look like this. This is a very interesting battery to study and a very good battery to show people to explain how batteries work. because it has all of the different kinds of battery reactions in it. The cathode is an intercalation reaction, and the anode is a conversion reaction, where you get zinc turning into zinc oxide. So here is the same plot as on the last slide, but it's in color. And this data was taken while the battery was being discharged. So here we see the two biggest reflections of zinc in the anode, and this is the biggest reflection of MnO2 in the cathode. And as I discharge the battery, here's what happens. So in the anode, I see two more reflections here start to form against the separator, and they're propagating backward into the anode bulk. So that shows me where the anode discharge reaction is happening, exactly where it's happening. It begins at the separator and then starts to happen further away from the separator. Now I'm going to play the video again, and let's focus on the cathode. So here's the cathode reflection, and we see it's moving to the left. And it's moving to the left. Yes?
Professor John, sorry to interrupt. Are you playing some video or something?
Yes, I am. Is it not showing up?
No.
Is my screen still shared?
Yeah, this is operando tomographic EDXRD.
Oh, but the video is not coming through.
Yes. AA discharge at 560 milliamp. EDXRD control cell, right?
Okay. Is the video playing now? It's not, is it?
No.
Okay.
There's some delay actually, but yeah, you can probably show after the talk.
Okay. Well, that's all right. I'll just move on to my next slide. That's my most. It's a very impressive slide that shows things moving around in the battery while it's being discharged. But the Google didn't like it, so we'll move on. And so, for example, with something like that, I can discharge 6 different batteries at 6 different rates, and this is the voltage of the battery while it's being discharged. Voltage falls in a battery while it's being discharged. And so if you discharge at a high current, you get less voltage and you get less capacity out of the battery than if you're at low current. So we did this experiment where we did 6 different currents and looked inside of the battery and saw several different distributions of materials inside the battery. And this was an interesting result. And the one that I liked the best was the 143 milliamp discharge, which was this one right here. And we looked inside the battery and saw that the cathode was, after it discharged, divided into 2 sets of materials. The part of the cathode nearest to the anode looked like this, and the part of the cathode furthest away from the anode looked like this. And we repeated that experiment several times, and it kept happening. And these batteries were made by Duracell. And then I went to Duracell and I gave a seminar to Duracell, and I showed them this. And I said, did you know that this was happening inside the batteries? And they said, no, we were not aware of that. So this is a good way to see things inside of batteries that may be difficult to see otherwise. So then what we did was in the discharge curve of these types of batteries, here this red curve is a discharge curve, and there's a dip in the curve right here, which you may or may not be able to see. But the dotted line shows the first derivative, so you can see the first derivative changes right there. So that's an inflection point in the curve. And no one had ever talked in the literature before about what that inflection point was. So we tested several batteries and did our EDXRD technique on them while we were discharging through that point. And that point was right here. If our data begins with the red and goes to the violet in the black, we see this peak, and then a second shoulder begins to form right there, and then after that, another peak starts to form. And right there, when you have that shoulder in between the two peaks, that is a phase change from the MnO2 material to an MnOOH material. And once that happens, then you get a whole bunch of other materials forming inside the battery. And it's this phase change right here that makes MnO2 non-rechargeable. So that's why these types of batteries are non-rechargeable.
Professor Josh, sorry
Yes,
to
sir.
interrupt again. So now you are in which slide? Because I'm looking at tomographic analysis post-discharge.
Uh-oh, it looks like we've frozen.
Mm-hmm.
Here, I'm going to unshare my screen.
Yeah, I think.
I'm going to unshare my screen. Okay, here I am back. Do you see me?
Yes.
Okay. Now I'm going to try to share my screen again. It looks like the video might have broken things.
Okay.
So now I'll share my screen again. Okay,
Yeah.
it looks like you have my screen. And I'll go back down here. And I will not play a video again.
Yeah, I think this we can see. I think we can probably present like this.
Okay,
Yeah.
this works.
Mm-hmm.
Okay, so MnO2, it's a very common battery material, and it's not usually rechargeable, and we want to make it rechargeable. So we want rechargeability of this battery material. And there are two ways to make this battery material rechargeable. Let me figure out how to advance my slides in this view. Okay. One way is to cycle the battery in a very shallow way. And so we have done that. We've cycled the battery in a shallow way. And we published a paper on this, and it was written by Nilesh Ingale, who was a graduate student at City College of New York. And this was the basis of the company Urban Electric Power that we founded back in New York. But then you can also cycle the battery through the entire discharge reaction of MnO2. And this came from a paper published by my colleague Gautam Yadav, and we published it in 2017. And we did this by adding bismuth and copper additives to the battery. And so that's what we want to understand, is why adding bismuth and copper additives to the battery helped our rechargeability. Okay. So now I'm moving on to the part of the talk about MnO2. So I just showed a little bit about MnO2. So a zinc MnO2 battery is usually considered to be a non-rechargeable battery. This is a AA type battery, AAA type battery. And all of the materials that are in the battery are very inexpensive. They are also very safe. The only thing that's unsafe in the battery is the electrolyte, which is a strong base and would burn you if you got it on your skin, which I don't recommend you doing, but that's the only thing that's unsafe about the battery. So safety and inexpensive nature of the materials are both very important if you're going to make batteries to back up solar and wind power. And this is because solar and wind power, if we're going to put them in the grid throughout the entire world, will require a lot of batteries. Those batteries have to be very big, and the batteries have to be very inexpensive in order to make that work. So here is a plot that was published by not us, but some people at MIT, and it shows different battery chemistries. So lithium-ion batteries are right here. That is a graphite lithium cobalt oxide battery. It shows that it was invented around the year 1990. And if you consider the cost of the materials in the battery, they're about $100 per kilowatt hour. So that is the y-axis. And notice that the y-axis is logarithmic. So these are lots of different battery chemistries. And there's an argument to be made that you will not make batteries to back up solar and wind power unless they are below this dotted line right here, because you have to be that cheap to make the cost of electricity work. So if we look below that line, what do we see? Zinc iron, iron iron, iron air also, sodium nickel chloride, zinc bromine, sodium sulfur, and zinc MnO2. Zinc MnO2 is the chemistry that I just talked about. So these are all very inexpensive materials that you can find on the periodic table. Sodium and sulfur are by far the cheapest. So if you want to make cheap batteries, you work in this area down here. So how to make zinc MnO2 rechargeable, that's what we want to find out. All right, I'm going to skip a slide and go to this one. So the reason zinc MnO2 is very inexpensive is because zinc and manganese are very inexpensive. If you look at the materials in lithium-ion batteries like cobalt, like nickel, these are $13 to $15 a pound. Nickel is $6 to $9 per pound. These are expensive materials. Interesting side note, when I used to work at City College, our market that we were always looking to serve was India. And so I used to always give these values in Indian money. And in the years since I left the Energy Institute, I've forgotten all of those. So now I have to do it in dollars, but I used to do it in rupees. So that's cost of batteries. Also safety of batteries. Let me show you, let's see if this video can play. Here is a lithium-ion battery safety demonstration. So here's a lithium-ion battery. Let me know if you're able to see this. Someone is poking the battery with a knife. And there they breached the battery. Now we're getting a reaction. There, some water and some air got into the battery, and that's what happened. All right, so were you able to see that? Hope so. So that's what happens when a lithium-ion battery is opened. So that kind of battery is in your cell phone. So those are not the safest batteries in the world. So imagine a battery like that. If your cell phone catches on fire like that, you can just throw your cell phone and walk away from it, and you'll be fine. Imagine if a battery that was in a shipping container next to a solar array caught on fire like that. That's a very big deal, right? So safety of very large batteries is why we are interested in water-based batteries, not like lithium-ion batteries. So that's why the zinc MnO2 chemistry is good for us. Okay, now MnO2 is a very complicated material. So MnO2 is its molecular formula, but the Mn and the O atoms in the material can be arranged in many different ways and have the same chemical formula. And this is called polymorphism. So these are different polymorphs of MnO2. There's alpha MnO2, beta MnO2, gamma MnO2, delta MnO2, lambda MnO2. And you see these have different arrangements. Now, these materials, the alpha form has these holes in it. And as a battery material, it works because you put ions into those holes. This delta MnO2 down here has layers. They're sort of holes that are very, very long. And ions go into these layers. That's how the cathode battery materials typically work. So our batteries, when we make MnO2 rechargeable, they cycle as this layered type delta MnO2. And the reaction is actually somewhat complicated. This is a cartoon of the reaction. You actually begin with this material, take it through a formation cycle, and then it forms this layered material. So these are the layers right here, and the ions go in and out of the layers. So this is the cycling reaction. And these yellow balls are the ions, and as you charge and discharge the battery, the ions go in and out of the layers. Okay, so we've used our EDXRD technique to look at what's happening inside of the battery when we have the bismuth and copper additives in there. And I showed before that on this part of the discharge curve, we got this material, this Mn3O4, which makes the material non-rechargeable. But if we put the bismuth and copper additives in there, we do not get that material at the same part of the discharge curve. Okay, so the bismuth and copper additives, which make the MnO2 rechargeable, work because this material does not form, right? So now what we're trying to do is figure out why that is true. Why does the bismuth and copper cause that not to form? Now we have some, so here is our understanding of the reaction mechanism right now. So these are the layers of manganese dioxide. And here we have the ions in between the layers. And these very small purple ions that I've drawn right here are Bi3+, so bismuth cations. And our hypothesis is that these sit between the layers and hold them together like pillars, right? So imagine pillars in a building. If you want to hold up the second floor of a building over the front door, you put some pillars up and they hold the structure together. So as the battery's discharging, these pillars hold the material together. And then at the very end of discharge, the pillars come out and the material comes apart, and then it forms a second layered structure. This is just a hypothesis. What we want to know now is this what's actually happening? So these are atoms inside of the battery. So we're using our operando, our materials characterization techniques to see if we can establish this. Right. And we've used a different kind of experiment recently, not using a synchrotron, but using Raman spectroscopy to understand this. The reason we did that is because during COVID, all of the synchrotrons were shut down for about 1.5 years, unless you were studying the COVID virus. So people who were studying batteries were not a priority at all of the synchrotrons around the world for about 1.5 years. So we were not able to access the instruments, although people who were studying the spike protein structure of SARS-CoV-2, they were using synchrotrons to figure that out. So we had to come up with other ways to do work during the COVID lockdown. So we had a Raman's spectrometer. And so we put the bismuth additive in and also took it out. And as we charged up the batteries, we saw a big difference between whether the bismuth additive was there or not. This is a charge without the bismuth additive. And we see one, if we're going from bottom to top of the curve, we see one peak. And then a second peak forms at the very end. But here, if we have the bismuth in there, we see two peaks from the very beginning. And these are both there all the way through the charge. And these two peaks show us that the layered structure is there throughout the entire charge. And without the bismuth, it's not. So this led us to hypothesize, if I go back here, if we're going backwards through this reaction, the bismuth helps this structure form very quickly. And so this layered structure is present almost all the time through charge. And without the bismuth, it only forms at the very end. So perhaps the bismuth pillars this structure and helps it form very early. So that is now what we are trying to figure out. We're doing some other techniques to see if we can spot that and synthesizing a bunch of materials. And then we're also working on zinc to couple with these materials in rechargeable batteries. Okay. Now in my last part of my talk, I spent a lot of time, I lost a little bit of time to the video problems, so I'm just going to talk very generally about this. So this is about all solid state lithium batteries, totally different kind of battery, and this is perhaps the future of high energy density power sources for portable power and transportation. So electric vehicles, in order to make them cheaper, safer, and better, we need better batteries to go into them. So to make better batteries, some people believe we need to remove the solid electrolyte and put in the liquid electrolyte and put in a solid electrolyte instead. So here's a schematic of a battery, a typical lithium-ion battery, where you have a relatively big anode coupled to the cathode. And if we replace the liquid electrolyte with a solid electrolyte, we may be able to replace this anode with a simple foil of lithium. So here we have just a small foil of lithium that's replacing this big anode. And that's made possible by the solid electrolyte. So you see here the two schematics. The solid state one is smaller. So that shows the concept of making a battery smaller by using a solid electrolyte. That would allow you to put more batteries in the car and allow the car to drive further without a charge. The problem that we need to work on is that no one agrees yet on what this solid electrolyte should be. There are many different kinds of solid electrolyte. For example, sulfides, oxides, phosphates, and polymers. All of these can conduct lithium. So the ones that have the highest conductivity are sulfides. So this is a very famous figure from the scientific literature that shows the conductivity of different solid electrolytes. And this dashed line at the top of the curve is the liquid electrolyte found in lithium-ion batteries. And look, these solid sulfides have conductivities that are almost the same, and in some cases higher than liquid electrolyte. This is a log scale that's going across 10 orders of magnitude. This line is at 10 to the minus 2 Siemens per centimeter. Now I want to point out, this is pretty much the last point that I'm going to make. That is amazing. These are solid materials, and they conduct lithium ions faster than liquids. Conduction if you've taken transport phenomena, you know that diffusion in liquids, if you're talking about units of centimeters per second, diffusion is a 10 minus 6th in liquids. And in solids, it's 10 minus 10 or 10 minus 12. There's 6 orders of magnitude between how much motion happens in a solid versus a liquid. Yet, these materials conduct lithium ions as fast as liquids. That's incredible. Now, I want to tell you the bad thing about them. All right, so this is a plot that's supposed to convince you the good thing about sulfides. The bad thing about sulfides is that we don't just care about conductivity in batteries. We care about many other things like processability. Can you make a battery out of it? Thermal stability, stability with lithium, moisture stability, and all these other ones. Shear modulus, how strong is it? These sulfides, if you expose them to humidity, form hydrogen sulfide gas, which is poisonous, of course. So these are very non-moisture stable. They're also not air stable. They're also not thermodynamically stable with lithium metal or with cathode materials. That's the reason for these yellow boxes. So these sulfides have wonderful conductivity, and there are many other things that are not good about them. But most car companies around the world have a large effort in making sulfide solid electrolyte batteries right now because they are so conductive, and they would make wonderful batteries if we could work out the problems. So we're doing work to understand why they have these incompatibilities with battery materials. So we make these cells where we have the yellow solid electrolyte and we have the black cathode material of the batteries in there, and then we look around at the interface between these two things and try and figure out what's the matter, why are they not stable with each other, and we've designed different materials to increase the stability, and that's the blue right here, and we've gotten pretty good stability, better than the black and the red curves, but it needs to be up here to work in an electric vehicle. So we've improved it, but there's still a lot of work to do. We are also using synchrotrons, like this one right here, to look at these things. And that is ongoing work that's happening in my group right now. So now I'm going to stop, and I'm not going to talk anymore about the work on solid electrolyte batteries, because I want to take time to thank all the people in my research group, which are these people right here. And I want to thank our funding sources. So NSF, the United States Army, NASA, and Sandia National Lab, which is part of the US Department of Energy. And I also want to thank all of you for coming to my talk and for bearing with the technical problems that we have. And I would like to take any questions that anyone has right now. And thank you, Professor Patil, for inviting me.
Thank you, Professor Josh. I will read out the questions for you. Maybe, you please. So,
sure thing. I see there's some in the chat, but I haven't had a chance to look at the...
So, is the Butler-Volmer kinetics applicable for porous electrodes? Can the porous electrodes be designed using various materials, say combination of lithium cobalt oxide and manganese dioxide in a particular electrode?
Yeah, that is a very, very good question. So blends of materials. So one way, so academics research one material usually, right? So they'll invent a material and put it in the battery and say, that looks great, and try to convince everybody that that's the best material. Industry has a different view on how you look at these things. And industry also keeps many things secret. So if you're an academic researcher, you often don't know what industry is really using in batteries. So the way someone in industry will look at batteries is they'll say, well, we have these two cathode materials that both have good properties. Let's put them together and see what happens. And that's exactly the question, right? So whoever's question that is a brilliant question. That's what people do. So unless you're working with battery companies, they won't tell you how they've put materials together. So you have to buy batteries and then tear them apart and analyze them, and it helps you understand what industry is really doing. So say, for example, if MnO2 is very cheap and very safe, and lithium cobalt oxide is very, very fast, but also very dangerous and expensive, instead of trying to just use one or the other of those, you can put them together and get properties of both. As with most things in engineering, it's nonlinear. You don't just get a linear relationship. If we want a battery that has, the cost in between these two materials, we just put half and half in there. It doesn't work like that. You have to know what proportion to put them in, and you can think of many other things that if you're an industrial battery engineer, you would want to do. Say, for example, change the particle sizes of these things. Maybe put them in different ways, like you could put them in layers. Like if you're going to lay your battery materials down like a sandwich, you may put a layer of one battery material and then a layer of another. Or perhaps you want them all mixed together. You can have a hypothesis why those why to do one versus the other. Or if you're in industry, you could just try many different things and see what works the best. That's often the way they do it. So hopefully that's a good answer.
Yeah, thank you. So is this Butler-Volmer kinetics applicable to porous electrodes?
Absolutely, it is. It is. The problem is, so for someone like yourself who does computational work of electrochemical systems, Butler-Volmer kinetics, like, I won't reshare my screen, but it was a kinetic expression that was current is equal to e to the voltage power. So it's complicated. It's nonlinear in your boundary condition. It's a nonlinear equation. But also, it had two terms. So the reaction can run to the left or run to the right, usually. It can go forward or backward in an electrochemical system. And if you use a Toffel expression, that's just one part of the exponential. And Butler-Volmer is both terms of the exponential. And both terms are applicable in an electrochemical system, but your computation, it becomes very computationally expensive to put that complicated a boundary condition at every interface inside of your battery. So picture a boundary conditions happen at boundaries, and a porous electrode is made to make boundary almost everywhere. And so you have a very complicated system, and you have to deal with boundary conditions lots of places. So growing lithium dendrites, anywhere the lithium dendrite grows, you have the Butler-Volmer equation happening, and that interface is moving. And then if it branches, it'll be happening in all those places. And so people usually try to simplify that equation. So.
Yeah. So next question is a general question. Is there a way to estimate the shelf life of a battery by a simple experiment?
Yes. People usually try to estimate the shelf life by heating them up. So if you want your shelf life, if I buy a AA battery, it'll say something on it like 10-year shelf life. But they change the batteries every 2 or 3 years. So how did they determine it's a 10-year shelf life when they're developing batteries that fast? And they have a rule of thumb, which is probably a secret, and I don't know the details of, but you take the batteries and you put them into some kind of heated environment and try to make them fail, because high temperature makes every process happen faster because of the Arrhenius expression. And so just every degradation process, you try to speed it up. And then you can extrapolate what your room temperature shelf life will be from the high temperature. I think it's usually around 60 degrees C.
So next question is, do the polymorphs of MnO2 change when you put them in the use?
Yes, they do. So that's something I didn't really talk about, but I could give a very long and very deep presentation about the changes in polymorphs that happen inside of the battery. So, I said that our polymorph is a layered polymorph and that it cycles as layers. But the layered polymorph of MnO2 is not a commodity on Earth, right? So industry, the industry of the world does not make a high tonnage, many, large mass of that material. But the gamma form of MnO2 is a commodity chemical, which is made many, many places. And so it is the cheap chemical to buy. And so what we do in order to use that material is we put it in the battery and then we cycle it, we discharge it and charge it. And when it charges back up, it becomes the layered form, and then it cycles as that layered form. Now, the layered form cycling, the layered form is even different because I showed that it maybe has those pillars in it. So that's one difference. How many pillars? Where are the pillars? You can think about where the pillars connect, right? So if there's an ion that's pillaring those layers, does it, if that ion were to look up and down, would it see a manganese atom above and below it? Or would it see an oxygen atom above and below it? Or would it see a hole above and below it? So there's vacancies in these layers. And the vacancies, if you were to take one of the layers and look at it, you would see a pattern of vacancies on it. And that pattern of vacancies is also something that changes the identity of the material. So these materials can get very, very structurally complicated. And the more complicated they get, the harder it is to probe and find out exactly what they look like.
Incidentally, my student from IIT Mandi, she had given a PhD synopsis today. So her work was on polymorphs of MnO2 by
Wonderful.
Density functional theory, DFT. So she
wonderful
of DFT calculations.
We have worked with someone who does DFT in New Mexico. Here, we have a colleague who does DFT of MnO2 polymorphs, and he makes us the energy, the energies of all of the materials. But one of the important things about the layered polymorph is it's hydrated, so it has water in between its layers, and so putting the water in there is one, like, is the water there or is the not water there? That's one complication. So I would love to talk about DFT of polymorphs of MnO2.
Sure. So next question is about mechanical degradation models. So can we use mechanical degradation models, say fracture mechanics, in the battery to predict the shelf life?
To predict the shelf life, I don't know. The battery itself has many failure modes, and you will have different failure modes depending on what the battery has experienced. So shelf life, like you said, shelf life probably doesn't involve any fracture, at least of a zinc MnO2 battery. Shelf life probably involves surface poisoning. So like you get reactions at surfaces, and like I said, it has lots of surface inside of it, and so more and more surface reactions happen, and the battery degrades that way. Another common way that batteries degrade in a shelf life sense is the case just fails and the water evaporates. So that's another common way for batteries to fail. Fracture mechanics. Now let me talk about fracture mechanics, which is something I know very little about because I'm not a mechanical engineer. I'm a chemical engineer. But when the battery is cycling, so say a lithium-ion battery, this cathode material is particles, and those particles are in a porous electrode. So you have particles. The particles, all right, now imagine a particle. That particle is also made up of particles. So it is an agglomeration of crystallites. And those crystallites could have grain boundaries or they could be single crystal, but they are, small, crystallites of material, and they're all agglomerated together. Now that undergoes the battery reaction, and the battery reaction is intercalation of lithium ions. So Li pluses go into this material, and then Li pluses come out of the material. Li plus, when it sits in the layers, it causes the layers to come together. Protons cause layers, in the MnO2 battery, the protons cause the layers to come apart. Li plus goes in and makes the layers come together. And these are there's different reasons why this is, but the layers are negative, and when the lithium goes in, it screens the negative charges and causes them to come together. So the layers, as you're cycling the battery, are constantly going in and out. And you have to imagine that these layers are in crystals that come together in these crystallites, and then the crystallites are agglomerated into a particle. And so as these layers at the atomic scale are getting angstroms closer together and apart from each other over and over, their volume changes. And so the volume of the particle changes while all of this is happening. And then these particles are packed together into a device, and the device has some compression on it. And so you have swelling inside the battery as you're cycling. This causes particles to fracture. So the particles will undergo fracture as this is happening. So that's like a use failure as it's cycling. And there's a group at Virginia Tech here in US, the Lynn group. And they do these experiments and show fractures in these materials, and it's fascinating to see how these happen.
Sure, thank you. So last two questions. MnO2 with the bismuth seems interesting, but Bi is a rare earth material, as I understand. Will this increase the cost in future?
So I don't know. Rare earth. I sometimes don't know what is a rare earth and what isn't. I don't think they're a rare earth, but I think rare earth sometimes depends on what your use is. So lots of lanthanides and actinides, those are rare earths. I don't think of bismuth as a rare earth, but it is a very big element, and it does have potential to be an expensive element. If you know Pepto-Bismol, right? Pepto-Bismol is the pink stuff that you drink if you have heartburn. It's a medicine, and it's called Bismol, B-I-Smol, because it has bismuth in it. Something I never realized until I started working with bismuth. So it's in a common over-the-counter medicine that's not particularly expensive. So it doesn't have to be expensive. The amount of bismuth that we use is very small. It's less than. It depends, but it's less than 1% of the other of the transition metals that are in the cathode. So if you have 100 manganese atoms, there's like one bismuth atom. So it doesn't increase cost too much. Now, if there was a battery in every electrical substation in the entire world, and if we succeeded and they all used bismuth, maybe then there would be a big demand and the cost would change and we'd have to look for another solution. Okay.
Yeah, thank you. So last question, Professor Gallaway. So thank you for the wonderful talk. My question is, are solid electrolytes less prone to thermal runaway in comparison to liquid electrolytes? Have you investigated the thermal safety of solid electrolyte batteries with aging?
Yeah, that's a very good question. And that's a thing that a lot of people are spending a lot of effort to look at. We are not experts in thermal behavior, so we don't look at that. We tend to look at mechanisms. So we look at like mechanisms of how the electrochemical reaction is happening. But thermal runaway, the concept of thermal runaway is because, say you get a short circuit, like say here's the anode and the cathode of the battery, and you get a lithium dendrite that connects them. You get a lot of current flow through that very small connection. That produces a lot of heat by Joule heating. That heats up the battery. And then in a standard lithium-ion battery, there's an ignition temperature that's very low of the electrolyte. And so then it becomes autocatalytic and explodes, and that's what caused the fire that I showed in my video. Now, the thought is that shouldn't happen in a solid electrolyte because the solid is not flammable in that same way. However, the dendrite problem still exists. So, it was speculated, some years ago, 20 years ago, that you could make a solid electrolyte that would be so strong that would stop lithium dendrites from forming in the battery. And it turns out that lithium dendrites are I don't know the current research on it, but can you make something that's so strong that it can stop a lithium dendrite from growing to the cathode? It's an open question. So I do know that they use solid, brittle, high Young's modulus materials, and the lithium dendrites will grow along the grain boundaries inside of the solid material and still short it. So even if you have very strong materials, the dendrites will still short. Then the battery heats up. I think it's not as big of a safety problem, but it still is very bad for the battery. So it doesn't necessarily explode, but it still kills your battery. So this is something that people, this is a very important problem to look at. So hopefully that's a good answer for that, although I wouldn't say I'm an expert on that particular thing.
Thank you, Professor. So there is one query regarding safety. Current battery technology in terms of safety, how mature it is? A short answer.
Well, I mean, safety is an ongoing problem, but you know, it's not immature. I wouldn't say it's mature, but Tesla electric vehicles, like one of their big innovations was they used very standardized batteries in battery packs, and they had control systems that if you have lots and lots of battery cells in a battery pack, one of them is going to fail sometime, and so you have a way to monitor these cells and to shut down the failing cells and keep the entire pack healthy. So people do know how to do that. I think lots of people work still. We don't know yet how to build the best battery pack, because we don't know how to build the best battery cell yet. As people are making new types of battery cells, they have to make new packs to go into new cars, and then you have to have new controls and new safety for all of those things. So it's an ongoing process. But I think people do kind of understand how to manage safety in a battery pack.
Thank you, Professor Josh. So we come to the end. I think that's the last question. So we would like to heartily thank our guest speaker for the TREES Talk 12, Professor Josh Gallaway from Northeastern University, USA, for his invaluable time and a good Friday morning for him. Thank you, Professor.
Thank you very much. It was an honor.
Yeah, thank you. We also like to thank the audience for their questions and an interactive discussion. Thank you all for joining.
Have a wonderful evening.
Thank you, Josh. See you. Nice seeing you after a long time.
Dharwad, it's wonderful to see you. I hope everything's great. It was wonderful to see your kids, and yes. Mine are gone, or I'd show you them.
Oh, sure.
All right.
Thank you.
Take care.
Bye.
Bye.
Sir, thank you very much for this is Ayyappan.
Oh, hi, Professor Satya. Yeah.
Yeah. I'm fine. Thank you for letting me know this event. Yeah.
Yes, thank you.
Please let me know in future as well. Yeah, I'll be happy to listen to those.
Yes. Okay. We are trying to have some series of talks on battery-related work. Trying to put some speakers related to that in our TREES talk.
Okay.
We are storing this online as well in YouTube. The YouTube channel. So you can look at the previous editions also.
Oh, is it? Okay. So it's the same of GCoE-ACE?
Yes.
The same name.
Yes, it's the same name. TREES talks.
Okay.
It talks on renewable energies, empowering Earth and sustainability.
Oh, okay. So it's a 12th one. Okay. Yeah.
Okay. Thank you. See you again.
Yeah.
Just come to Dharwad.
Please, yes, definitely. Looking for that. Yes. I mean, looking for such opportunity. Thank you. Yeah.
Thank you.
Yeah.
Thank you, Professor Ivankar. Oh, you are not audible.
Yeah, I'm at home, sir. I'm at home.